Hello everyone, my name is Badram, and in this video I'll walk you through how to do machine learning regression using PyCaret. If you already don't know what is PyCaret and how to install it, please check out the previous two videos and then come back here. Okay, so as we talked about it in the introduction video to PyCaret, there are 25 underlying regression models available in the PyCaret Python library as of today, which is December 2022. We are gonna go over all these models, and I'm not gonna talk about the theory behind them. If you're interested to know more about the theory, please check out my crash course in machine learning, simply explained, which I go over many of these models already. But in this one, I'm gonna showcase an example, and basically I'm gonna walk you through the final predictions by the model. And we're gonna do more. We're gonna ensemble these models, we're gonna stack them, we're gonna blend them, and we're gonna make a best performer among all these models. Okay, then, and here's again at the very high level what we need to do. We just simply need to load the data set and then set up the environment and simply run this line of code, compare models. So behind the scene, if I do compare models, those 25 models are going to be run, and the cross-validated performance metrics are going to be calculated, and you can save the top 3, for example. You can save the top 5, and then you can blend them. You can ensemble some of those models, or you can literally stack them together. Then we're going to look at some predictions and finally save the model, and I'm going to show you how to deploy. Okay, so here is where those notebooks are hosted. It's in my GitHub account. So I made a new repository. It's called Platforms and Tools. And in that Platforms and Tools, you should be able to find a folder called PyCaret. So let me walk you through that one. So this is my GitHub account. Again, there is this Platform and Tools. If you go inside that Platform and Tools, this is the PyCaret folder, and you're going to see a demonstration for classification, regression, time series, and that's it. And this is the PDF that I went over in the introduction part. So if you want to see what are the available models in PyCaret and etc., you can simply check out this PDF. Okay, so without further ado, let's go do the regression part in this video. Okay, so let's go ahead and click on this PyCaret regression demo, IPy notebook. So for this regression example, I'm going to show it to you how to do it on Google Colab. And for the next one, which is classification, I will run it on my local computer on VS Code. So if you don't know how to run Python code in VS Code, you can go ahead and check out my YouTube channel. There's this playlist. So if you go to the platform and tools, there's this playlist called VS Code. And here I'm going to show you how to install VS Code and how to do Python coding and install packages and extension and everything from scratch. So I highly encourage you to use VS Code if you want to do any kind of programming, for example, Python, C, C++, Julia, Java, you name it. So it's one platform, one interface, which you can do multiple programming using literally one interface. Okay, so again, I'm going to showcase the regression one in the Google Colab. So let's go ahead and click on this, open in Colab. It should navigate you to this Google Colab. Okay, so I'm gonna go ahead and copy to my own drive because again, this is Google Colab. You cannot make changes here, or if you make changes, you cannot save them, right? So if you wanted to make it your own version, make sure that you copy it to your own drive. First check you're in the right Google Drive account, and then go ahead and copy it to your own drive. Okay, so it's creating a copy to my own drive. Now this version, which is going to be named copy of PyCaret regression, is mine, and now I can make changes. Okay, so I'm going to go ahead and close this one because we don't need it anymore. And now we can run things on a virtual machine that Google Colab is going to provide us. Okay, so the first thing first, I'm going to go ahead and connect. So for this presentation, I'm going to use a simple CPU because I'm going to work with a subsample of the data, which I don't know, sample size of 1,000, just for the purpose of illustration. Because again, making sure that 25 models, regression models, are being run under the hood If your data set is large, it's going to take time, sometimes forever, right? So, but for this presentation, I'm going to work with a very small subsample of the data, let's say 1000. Okay. All right, let's start with the links for resources. Well, this notebook is a combination of two notebooks that is already coming as tutorials with the PyCaret library. You know, the beginner version and an intermediate version. So I'm using another data set just to make sure that you're seeing a different data set from the PyCaret tutorial. And then we are going to focus on PyCaret 3.0 documentation API. Let me go ahead and click on it. So this is basically the API documentation that we're going to work through. We go to regression, and remember, you know, in the introduction video, it talks about different steps, right? Setting up the experiments, creating models, comparing models, and etc. So we're going to see how each of these functions are going to look like and what are the attributes that we can play around with. Of course, if I want to talk about all the details, it's going to be at least a couple of hours of video. So I'm going to try to make it as short as possible, but at the same time, I will highlight things that will help you to, I don't know, somehow ace the Kaggle competitions or go to the top 5% of the Kaggle competitions, okay? So let's keep this one open, and as we go through different functions, I will go back and forth between the documentations and what we're doing in a notebook. And as you can see, each of them has so many attributes that you can play around with at your own pace. Okay, so again, I'll try to keep it as short as possible, this video, but these are the things that we're going to cover. So we're going to see how to get the data, how we import the data from PyCaret, and what is basically the list of the data set is available in the PyCaret library. And we'll talk about normalization, you know, how to normalize and scale the data set, transformation, you know, target transformation. Basically, we can transform the feature space and at the same time the target variable as well. We're going to see how we can play around with ignoring low variances. So for example, we're going to remove features with a statistically insignificant variance to make an experiment more efficient. So we can come up with thresholds. So for example, we can say if the variance is 0, drop them. We will see different methods for removing multilinearity. We'll talk about grouping features, you know, combining error levels, bin numeric variables, and most importantly, setting up the environment. And as you saw, there are so many features we can play around with in setting up the environment. And then we get to create models, tune models, plot models. This is a regression plotting, so we're going to see what is available when it comes to regression plotting. And finalizing the model, making predictions, and this is a cool part. So this is the part that's going to help you, again, go to the top 5 or top 10% of most of the Kaggle competitions, right? We will be talking about ensembling and stacking and blending, you know. And then, yeah, we're going to save the model, and basically that's it. Okay, so I'm going to go ahead and run this line, pip install. I think if you do pre or without pre, it's going to go ahead and install the 3.0 version in the Google Colab. So I'm going to go ahead and run this line. This may take 5 to 10 minutes. Well, let me see. Okay, so if you get this error, it is very common. Probably it's because you're copying and pasting from other notebooks, and sometimes it just complains. So you should go ahead and type the entire thing one more time. So I'm going to do pip install PyCaret and then full. Okay, so I'm going to go ahead and erase this first line. Okay, this should do it. Okay, yeah. And as I said, this is going to take 5 to 10 minutes. So I'm going to let this run. And at the same time, I'll walk you through to the rest of the code. And by the time that we are halfway through the code, halfway through the notebook, I'm going to come back and see if the installation is complete. And I'm going to showcase some of the features maybe down the road. Okay, so let's say we are done with the installation, and then we check the version of the PyCaret. So we're going to do PyCaret utils version. Let's look at the version number. Hopefully we are going to get 3.0. If you do not get 3.0, you have to go restart the session and then do pip install dash pre PyCaret full, right? But hopefully, I think we're gonna get the 3.0 version with this without that pre PyCaret thing. Okay, now how we are gonna import the data set? So we're gonna say from PyCaret.datasets import get data. So this is a function that we use. If I do get data, then quotation index, it's gonna give me all the datasets available that comes with the PyCaret package, right? This is very good because you then, if you want to play around with, I don't know, regression, classification, anomaly detection, you name it, you can now know where you can find a data set, right? So yeah, just look at that. This is the name of the data set, and then this is the data types, you know, multivariate, univariate, if it is time series, or again, the most of multiple and univariate makes sense for time series, right? So for example, if you scroll down to the regression, and then you may find a univariate, which we don't here, so it means that we don't have a univariate time series here, which is fine. You know, we have a multivariate, we can treat it as univariate as well if you want. Okay, but again, there are lots of data sets for classification, for multi-class classification, for clustering, for NLP, natural language processing, and for regression analysis, right? And again, the name of the data set, the name of the variables, number of the attributes, and if there's a missing value or not, right? And of course, number of the observations. So the data sets are relatively small because, again, the goal is to use these data sets as a sandbox and play around with the features of PyCaret, right? Okay, so let's say we are going to work with this data set called bike. So this is a regression data set. The target variable is going to be count. I'm going to talk about the details of this variables. And then there are 17,000 observations, 15 features. Well, one of them is going to be target variable, and we're going to end up dropping 2 of them. And there is no missing value, so we don't need to be worried about how to treat the missing values. Okay, and yeah, so I'm gonna say let's save this data set as data set. This is an object, and call this function get data, and I need to just simply write down the name of the data frame, bike. Okay, let's look at the head of the data frame. Again, what we're gonna have here is a couple of the features, right? Bunch of features. This is a date, and we're gonna drop it from the model. Instant is basically the record index. We're gonna end up dropping that one as well. So season, this is it's a numerical categorical variable, right? It goes from 1 to 4, 1 for winter and 4 for fall. Then we have year. Then again, it's a categorical feature 0, 1. 0 stands for 2011 and 1 for 2012. Then we have month, goes to 1 through 12. We have hours, 0 to 23. We have holiday. So this is whether a day is holiday or not, right? Then we have weekday, basically the number of weekday, go from 1 to 7 or 0 to 6. This is working day. So it's a binary categorical variable. If it is 0 or 1, if it is a working day or not. Then we have weather situation. So again, it's another categorical variable. 1 stands for clear, 2 is for misty, cloudy, 3 is light snow plus light rain, and then 4 is for heavy rain, right? Then we have temperature and temp, humidity, wind speed. So these are all the normalized variables, continuous random variables. So for example, temperature is a normalized temperature in Celsius. Temp is normalized feeling temperature in Celsius. Humidity, as the name suggests, is a normalized humidity, and wind speed, again, as the name suggests, is a normalized wind speed. And this CNT stands for count, which is our target variable. Basically, that's the total rental bikes, including both casual and registered. Okay, so that's the data set, and now we can do EDA. Let me actually go ahead and pull up the slides that we put together for the introduction part. So if you go to where is it? Yeah, if you go to the platforms and tools, and then PyCaret, let's open up this PDF. Yeah, I want to show you. Okay, so here, Let me load more pages. Okay, remember we said that we can use PyCaret for EDA as well, right? Explanatory data analysis. So this line, I commented out because if I want to apply to the entire data set, it's going to take some time. So I'm going to go ahead and work with a subset of the data set by using the sample function in Python, and then replace my data set with only 1000 observations. And then when the installation is completed, I can come back and show it to you how does it look like. So basically you can say when you're calling the data set, remember we did get data by, we can also say profile is equal to true. So if profile is equal to true, it's going to do an automated EDA, which is based on Panda's EDA package. And at this stage on Google Colab, you're not going to get any error, but on your local computer, you may be prompted by you need to install the PyCaret analysis. So if you got that message, go ahead and do that. Go ahead and pip install PyCaret. But in Google Colab, I doubt. But again, we are going to double check. Once the installation is complete, we're going to come back here and see if it is running. Let me go back and see if the installation, yeah, it's still installing. As I said, it's going to take 5 to 7 or 5 to 10 minutes, depending on your internet speed connection and the virtual machine that you have been dedicated. Okay. So one downside about running PyCaret on Colab is if for whatever reason this get disconnected, I have to install it from scratch from again. So every single time that you want to install it, it's going to take 10 minutes. Or for whatever reason you want to leave the Google Colab idle for hours, then if you get disconnected, you have to install it again. So again, that's maybe the most important downside of using Google Colab free tier. For PyCaret, I highly encourage you to run it on your local computer as well. Okay, so then at this stage, we're going to do something which we usually don't do in machine learning, but with PyCaret, it's again, this part is optional, but it doesn't hurt. I encourage you to do that. And what is it? We're going to say that data set that was 1000 observations, let's go ahead and take 90% of it and call it data, and leave 10% completely out of this entire process of comparing models, tuning models, and etc., right? I'm going to call that 10% as data unseen. I'm going to call it data unseen. So this means that once I'm done with this finding, let's say the best blended model, cross-validated and etc., I'm gonna then make predictions for the unseen data, and I'm gonna say make that prediction on the 10% of the data. Do not confuse this one with the train test thing that we usually have in the scikit-learn package, right? So we're gonna still have the train test thing, because at the end of the day, when you want to compare models, you have to compare their performance in the cross-validation or in the test set, right? But this is completely different. The goal is to somehow mimic what we see in real life, right? So imagine you're doing time series, you have extended all the data as of today, and you don't know what's going to happen tomorrow, right? You wait and you collect more information. So you want to apply the model to something to something that the model has not seen before. So we're going to call this 10% of the data unseen. Then we're going to say, okay, now I have 900 observations in the data and 100 observations in the data unseen. Okay, so this is again the head of the data set. In order to figure out what should be the type of the variable, we can look at the number of unique elements of each variable. So this is the easy trick to figure out what variable should be what type, right? So remember, we had 900 observations, so the number of instances this is observation is going to be 900. We're going to drop it later on. Again, we talked about this date, which we're going to drop. We're going to drop it here because we already have year, month, and hours. So we have already extracted everything we needed from that date, so we don't need to include it again in the model. So as you can see, season has 4 values, so it means that it should be categorical, year should be categorical, month should be categorical, hours should be categorical. but we have 24 categories. Maybe we want to group some of those hours together, right? We want to group them by 4 hours. So this is one thing we can consider. Holidays, categorical, weekday, working day, and weather situation, all categorical, right? And then temperature, of course, these are normalized continuous random variables, so they have 45 unique values, 56 unique values, and 73 unique values for humidity. They should be left like numerical values. All right, so then I go ahead and make these 3 lists. So the list of categorical variables, the list of numerical variables, and the list, I just call it ignore. These are the list of the variables that I want to ignore in the model, because in PyCaret you can pass something like ignore to the setting up the experiment, and when you're setting up that experiment you can simply ignore those things, right? All right, so let's go to the setup part. So let me quickly go back and see if the installation is completed. Yeah, it's not completed yet, so this is taking longer than I expected, so I'm gonna let it run and keep going down the notebook. Okay, so setup. So now this is a point that I want to go back and forth between the notebook and the documentation. So this is the setup, right? So this function initializes a training environment and creates a transformation pipeline. So setup function must be called before executing any other function. So this is your first task. You have to set up the environment or set up the experiment. And one cool thing about PyCaret 3.0 is it is more object-oriented API, so it's more consistent with the Python thing. This means that the settings are linked with an object. So it means that I can have different experiments. I can call it experiment 1, experiment 2, and for example, experiment 1 is a regression experiment that I'm not pre-processing any data. Experiment 2 is the one that I'm pre-processing the data and maybe normalizing and doing different things. Experiment number 3 is pre-processing plus, for example, the removing outliers and some different things, right? So the cool thing is that we can have different experiments, okay? And different experiments is going to become handy in the Python 3.0, because in the older version of, PyCaret. In the older version of PyCaret, you had to, if you want to do different experiments, you had to run through the entire notebook. But now we can simply, at the very top of the notebook, we can define our experiments. So here, for example, I'm going to say no pre-processing. This is my experience number 1, exp1. And by the way, I have to import everything from this PyCaret regression. So when I do from PyCaret.regression import star, it means import everything, including this new thing in the PyCaret 3.0, which is regression experiment. This is a class that you can only have access to in PyCaret 3.0, not the older version. So if I import everything, it's going to be part of that import, right? So now I can say, let's treat this as our ordinary object-oriented thing in Python, right? Now I have an object, which is an experiment. I'm going to set up that experiment on this object, right? So off of this object, I'm going to make setup. I can create models, I can compare models, I can tune models for this experiment, right? So I'm going to say, okay, let's set up this data. Remember, my data is now 900 observation, because this is the way that we defined it. I'm going to say ignore these features. So this is one of the features of the setup. When I say ignore features, and this is a list, remember I said already ignore these two. Then target, of course this is the most important thing that you have to pass. This is your target variable. In our case is the count, number of rental bikes. Then session ID, this is just like a random state in scikit-learn package. And by the way, I think in the introduction video we talked about it, the PyCaret is heavily based on scikit-learn package. For example, for time series is heavily based on SkyTime package, right? So the underlying package is very, this one, PyCaret is very consistent with the terminology and what we use in scikit-learn, machine learning package, okay? Train size, let's say 70% train size, 30% test size. Remember guys, do not confuse this one with what we just created here. This is a holdout data set, or we call this data unseen. And now that was 10% of the data. And now out of that 90% of the data, we are dividing it between train set and a test set. And PyCaret wants to call it holdout set instead of test set, okay? So again, these are just labels. As long as you know what you're doing, it really doesn't matter what you call it. You know, we have a train and test or holdout, and you can even call it validation set. And then something that we are doing differently here in PyCaret, which is unseen data. Then you can pass your categorical features. Remember, I created a list, I call it categorical. You can pass your numeric features. I created a list, I call it numeric, right? Now, this is my experiment number 1, no pre-processing. When I run this line, it's going to go ahead and set up that experiment for me. And now that experiment has been saved as exp1. Now, off of this, I can go ahead and compare models. I can go ahead and create models. I can go ahead and tune models. So for example, if I say experiment 1, create model, random forest, it's going to work with this setup, okay? So I'm going to go ahead and make another experiment as well. So let's call it experiment number 2. And here, I'm going to do it with pre-processing and more, right? So the setup is going to be slightly different for sure, right? So the target, session ID, train size, these are all the same things. But now I'm going to say, if I had NA values, which in this data set I don't, but just for the sake of argument, let's say we did have NA values for, let's say my numerical variables. I can say do numerical imputation, use average. So it's going to use average for all the missing values in the numerical, let's say, feature, right? I can replace this mean with median, with, there are some features that, some options that you can pick from in the documentation. I'm going to show it to you in a second. Categorical imputation, the same story. We can use mode, and again, different candidates that I'm going to show you the list here. And so this is a key part. Go ahead and pre-process this thing, right? So I'm going to say pre-process equal to true. Normalization true, remove outliers true, ordinal features not. Well, here I'm going to say none of those categorical features that I created are ordinal, right? So remember, none of these categoricals were ordinal, so it means that the order didn't really matter. Okay, so what else? So then this is going to take, so setting up this step is going to take longer compared to setting up this experiment, because this is no pre-processing with pre-processing. Okay, so again, I'm trying to keep this video as short as possible. That's why I'm not running these codes, right? And then, so before going to compare models, I'm going to go to the documentation and show you the setup, the options that we have. Okay, so basically this is our regression. Remember, regression experiment, right? And now we can, let's look at a bunch of them. For example, we talked about target, we talked about train size, test size, ordinal features, numeric features, categorical. We talked about these ones already. And for example, instead of ignore features, you can do keep features. Okay. Again, some of these are really straightforward. I want you to read it on your own. The pre-process, we talked about it. Imputation type. So for example, let's say for numeric imputation, we can drop them. We can use average, we can use median, we can use mode, we can use KNN for imputation, right? If you want to use, for example, linear regression for imputation, it is not available here unless you do it manually. Okay? And yeah, for categorical imputation, the same story. You can drop them. You can use mode, or again, you can provide your own thing, your own string. And what else? We have one-hot encoding, max level of one-hot encoding. So imagine, this is also interesting. So imagine you have zip code in the data, and you have, I don't know, 400 values for the zip code. And of course, you don't want to add the dimensionals. You have the data by 400 numbers, so you want to max it. You want to max it by, I don't know, 25. The default value is 25. And again, there's some details that you can play around with, so I just leave it up to you. But some cool things that we didn't talk about in that notebook is feature engineering. So let's talk about this feature engineering. Remember, in introduction, we talked about feature engineering. Here, we can do feature interaction. We can add polynomial features. We can do all these things, right? So let's look at the documentation. So By default, it's not doing the polynomial features, but you can go ahead and change it to 2, 3, 5, 10, whatever, right? Basically, you're adding polynomial features to your feature space. This is the low variance threshold that I was talking about. So for example, by default, I guess it's none, right? So basically 0, it means that if the variation is 0, just drop them. And yeah, remove multicollinearity with a threshold. Of course, we have to say if the multicollinearity is greater than 90%, let's go ahead and remove them. Numeric features, I think I gave you an example in the introduction one. So for example, for FICO score, you can do this numeric features. The FICO goes from 350 to 850, I guess, and then you can put them in different bins. And remove outliers, these are the methods for removing outliers. And yeah, doing transformation, the transformation method, you can do, I don't know, simple normalization or standardization. Yeah, again, simple normalization with z-score normalization, standardization. We can do PCA if you want to reduce the dimensionality of the data. For whatever reason, you want to work with a lower dimension data. When it comes to visualization, you can have more fun in 2 dimension. You can look at the PCA method, right? So interestingly, they offer kernel PCA as well, right? So we can do linear PCA and kernel PCA. And so again, if you want to get the theory behind these things that I'm flying over, is basically check out my conceptual videos, here, machine learning concepts. I talk about many of these things, not all of them, of course, because the list is very long. But down the road, I'm planning to keep adding to these things, to the machine learning concepts. I'm putting together a course, somewhat similar course for the deep learning, and I'll start releasing them by January 2023. Okay, I think, yeah, feature selection. Again, this is the feature engineering part. And yeah, the list literally does not end, and again, I want to keep this video short, so I'm gonna go ahead and maybe talk about 2 or 3 more. So maybe the more important one is this folding strategy for cross-validation. So by default, it's gonna do 10-fold cross-validation, and again, the default way of doing cross-validation is our ordinary k-fold, but we know that, for example, for time series, we should not use k-fold because we cannot shuffle the data, so we have to do time series cross-validation. And yeah, and this time series cross-validation is based on the scikit-learn package time series cross-validation, but you have to make sure that your scikit-learn is the latest version, because the older version of scikit-learn did not offer this time series cross-validation. Again, the default value for fold is 10. If you're not shuffling the data, if you're not shuffling the fold, sorry, the data is shuffled, of course, because it's random data. And use GPU, I think by default you don't need to do anything to use GPU, but for some models like, I think for light GBM you have to do something. Yeah, again, it's already enabled for XGBoost, CatBoost, but for light GBoost, it is going to be automatically enabled when the number of rows is greater than 50,000. And other than that, you have to do it manually. Yeah, that's pretty much it. Again, I think this is all the important things that I wanted you to know about the setup part. Okay, so now that we're done with the setup part, we go to the compare models. Okay, so that's the next one. Okay, so let's go back and let me go ahead and see if the installation is complete. It's still running. Probably yours is you are gonna have a better experience. I don't know, for whatever reason it's slowing down on me this much. Usually it doesn't take me more than 10 minutes, but if you get something like this, maybe you're gonna reset your session. I'm gonna keep working on this notebook anyways, because again, we're going through the codes, and if you had this same bad luck like me, you can run it locally on your computer. In my next video, I'm going to show you how to run this locally on VS Code. Okay. Let me see. So compare models. Okay, let's do the compare models, and I'm gonna go both the documentation and what I have in the notebook side by side, right? So the compare models, this function trains, and of course the, the options are fewer compared to setup. And as you can guess, the setup was the biggest chunk of what you're gonna do in PyCaret. The rest should be pretty straightforward. So the compare model function trains and evaluates performance of all estimators available in the model library. Again, for regression, as of today, there are 25, and we can go ahead and look at them. And just remember, when under the hood, the model is the PyCaret library is training 25 models. It's using cross-validation, by default 10-fold cross-validation, to report the regression metrics. So you can sort the models based on different regression metrics, right? So you can sort them based on R-square, you can sort them based on RMSE, whatever you want. You can, if you use the tag sort, and then you can simply pass it. So here, for example, we're using sort by default is R-squared. You can simply change it to RMSE, you can change it to MSE, and you name it, right? So let's go back, open this one. Okay, so I'm gonna go ahead and say, you know what, from my experience number one, so remember that experience number one was the is set up without pre-processing, right? So I'm gonna go ahead and save the top 3 performers, and I'm gonna save it like top 3 from experience 1. So this is a difference between PyCaret 3.0 and the older version. If you are used to the older version, remember now you have to call the experiments, not whatever you call it, right? This is the object-oriented part of PyCaret 3.0. So if I just run this compare models, like the documentation, it's going to give me error because it's asking for what is your setup. So I have to make sure that I set up an experiment before, and then I run this one. And if you want to have multiple setups, just make sure you're running like experiments, right? Like what I'm doing here. Okay. So then I'm going to say, again, by default, it's going to sort them by R-squared and keep the top 3. Okay. Number of select is equal to 3. So if you look at that, so maybe the most important thing that you want to incorporate here is the n number of selects, right? So include is the list of models, scikit-learn compatible objects that you want to include. You can exclude some models. You can, again, look at the fold. You can, well, the answers are going to be rounded up to 4 digits by default. Again, cross-validation by default is true. These numbers that you're seeing here, these are the cross-validated estimations, okay? And for those of you who may wonder why we need to do cross-validation numbers, because if I use the training R-square, it is absolutely cheating. If I use test R-square, then my prediction on the test set is not reliable because it's kind of another type of cheating, right? I don't want to test the model on something on the data that the model has seen. So we're going to do cross-validation. So cross-validation is basically using 10-fold or 5-folds of the data and trying to replicate or estimate the performance of the model in the test set by using the train set. Okay. So again, if this is still vague, please make sure that you check my conceptual videos when I talk about cross-validation. Okay, and where were we? So yeah, this is a sort thing. By default, it's going to sort by R-square. The number of select, again, to give me the top 3 models, give me the top 5 models. This budget time, this is interesting. If for whatever reason some of the models are taking longer than usual. I don't know, for example, you're doing XGBoost and LightGBM and it's taking longer, automatically it's going to drop them. Yeah. What else? I think that's pretty much it, all we needed to know. Yeah. Okay, so let's go ahead and see what is the output of this step, so of the compare models. Again, for this specific data set, we are looking at 900 observations in the train set, and we are running, it's a horse race between 25 underlying regression models, and surprise, surprise, XGBoost is the winner. In most cases, XGBoost will be the winner, especially if the dataset is large enough. So XGBoost will be your winning, and it's generally boosting methods. Look at that, XGBoost, Light GBM, extra tree regressors, GBM, gradient boosting regression, and random forest. So as you can see, this is the power of decision tree and ensembling decision tree, and which is not uncommon that you see these boosting methods at the very top of your machine learning regression models. So how can we improve this performance? We're going to stack a bunch of them together. We're going to blend them together. So this is how we can win some of the category competitions. We have AdaBoost, decision tree, lasso, ridge, and Bayesian, linear regression. Look at our friend linear regression, right? So if you're looking at the econometric side of things, so this is at best what econometric can do when it comes to prediction. Gives us an R square of, let's see, what is the R square? 36%. So this is a lot less compared to 83%. So if you're wondering what does it suggest, this is linear regression, R square of 36%, because the features are the same. We didn't add polynomial features, we didn't add interaction in the experiments, number one. The features are pretty much the same. So why is the huge difference between the performance of this model and this model? And the answer is that, so this is screaming at me that there is some nonlinear relationship nature in the data set, especially hierarchical nature, because my decision tree, the boosting models are performing excellent compared to simple linear regression. So again, I think at the very high level, analysis like this should help you to pick your right model. So this is, I'm talking about why you should use PyCaret, right? So don't use it blindly or just use it for winning Kaggle competitions. Sometimes a Kaggle competition, the single model is going to be the winning model instead of you blending a combination of top 5 or top 3 of these things. But it should gives you what's going on, what's going on behind the scene. When I see something like this for linear regression and I compare it to my boosting models, I realize that, okay, so there is this hierarchical relationship in the data. There is this nonlinear relationship in the data. All right, and yeah, ElasticNet, atomic regressors. I think I cover, many of these things. Maybe 3 or 4 of them I do not cover it in these conceptual videos, but the rest is covered. And I plan to cover, anything new. If you have any suggestion, if you want me to cover any machine learning models, just let me know. So remember, you run this compare model. This takes time, usually depending on the number of observations you have, but this is the step that's going to take the most time, right? And I saved the top 3. So our top 3 is XGBoost, Light GBM, and the ET extra tree regressor. So if I want to see what is inside top 3, I can just print it out. As you can see, XGBoost with these features, with these hyperparameters, and then I have my Light GBM and extra tree regressor. We can go ahead and change all the hyperparameters. We can tune the model and we can adjust it. Okay. All right. So here is the top 3 from experiment number 2. And remember, experiment number 2 was when I pre-processed the data. Again, the winning models are the same: XGBoost, Light GBM, and ET. But the performance-wise, surprisingly here, it seems that our XGBoost is doing 81.9% R squared. And here is doing 83.74 R squared, right? So it seems that for this specific data set, we didn't need to pre-process our categorical variables, right? Because remember, our numerical variables, our continuous numerical variables were already standardized or normalized. So it means that pre-processing the categorical features didn't help that much. If anything, it got worse. So for the rest of this notebook, I'm going to stick to my experiment number 1. But this does not mean that I could not play around with the experiments number 2 and make it better. Again, the rest is just the art part, right? You have to play around, try and error, different versions of pre-processing. Remember, the setup had so many things to do, right? So many options you could play around with for the setup thing. Here. So you can, based on experience, you're going to figure out what adjustment is going to work for your specific. You definitely need some domain knowledge, and the familiarity with the data set that you're working with, but this comes with time. Okay, so we are done with the compare model. Let's do create model. Okay, so again, this is my experiment number 2. We talked about this one. Now let's do the create model. So what is this create model? So this is a function that trains and evaluates the performance of the given estimator using cross-validation. So again, we are going to always use cross-validation, and now we want to say, okay, I get a sense what is the performance of the models, both for the pre-processed data, unprocessed data, and now maybe I want to dig deeper for the XGBoost, or maybe for some explanation purposes, explainability, I want to do random forest because I love the feature importance of random forest, right? Or you want to definitely look into your benchmark, your linear regression. So you can go ahead and create those models one by one, right? So I'm going to say, and I'm going to make an object, call it XGBoost. Again, be very careful in PyCaret 3.0. You have to make sure that this create model is attached to an experiment, right? Experiment number 1. And so that's simply, I call the name of the model, right? This is a model ID. And I think we talked about a model ID here, right? So if I go back, these are the model IDs, right? So XGBoost is model ID for that. And then, so this is my XGBoost. If I want to do linear regression, I simply write LR or whatever you want to call it, right? Call it linear regression, but this should be model ID, PyCaret model ID thing, right? I can do experience number 1, create model, linear regression, LR. So because this is the model ID. All right. So now I can see for this specific model, I can see the performance in different 10 folds. Remember, the default value for cross-validation was 10. So we go from fold number 0 to fold number 9. And this is literally our cross-validation for 10 different folds. And we can go ahead and report the average and its standard deviation. So this is important. The standard deviation is important because look at that. These are, for example, if I look at the R-square of the XGBoost model is 83.74. By the way, this is where the number is coming from. You see, in experiment number 1, it was 83.74, right? So this number is coming from 10-fold cross-validation, right? So 10-fold cross-validation. And this is the average value. And the standard error is important because sometimes you get a high R-square, but if the standard error of R-square is 10%, so it's not necessarily good, right? Even here, this standard deviation is not small. I get a model with 84-ish% R-square, and the standard deviation is also in the scale of 4%. Okay. The smaller, of course, the better. But always keep an eye on the standard deviation of the model performance. Okay, so let's see what do we have in the compare model. I think there's not much in the create model. Let's see. Again, you can get access to the model ID here, and then the cross-validation true. Let's see. Yeah, that's pretty much it. There's not much you can do in the create model. It's pretty straightforward. So the next thing is tune model. So imagine I created my model, call it XGBoost. And remember, guys, these are the untuned models, right? I'm going to say, okay, I want to see if my XGBoost can do better. So I will call it tuned. Well, I'm missing a D here. Tuned XGBoost. And again, if I want to call this tune model, I have to make sure I attach it to an experiment. So experiment number 1. Unprocessed data, and this is my model, right? So we created this model already. Look at that, we created this model already, and we are creating a tuned version of that. So again, it's going to do 10-fold cross-validation, and now, yeah, surprise, surprise, we got better R-square for a tuned XGBoost. So the XGBoost was the performance was 83.74. Now it is 84.39. Okay. So far I like the performance of this tune XGBoost, so maybe this is my winning model. Now we want to see if we can do better or not, so this is what I'm going to cover down the road. If you want to see what is inside XGBoost and inside tuned XGBoost, basically what happened in that tuning part, So this is what you can get access to the parameters. There are some other ways that you can look at the hyperparameters. If I use the plot thing, so I'm gonna say plot the parameters. So I will see all these the values for parameters and hyperparameters. And now let's look at the documentation before plotting things. Look at the documentation for tuning things. Okay. So tune model. Okay. So for tune model, actually there is something here that we can do, and that's the custom grid search. This is important. So first of all, you have to pass the name of the estimator, right? So for example, in this example that comes with the documentation, we are creating a linear regression model and we are tuning that linear regression model, right? In linear regression, there's not much to tune, right? Unless you are adding polynomial features and you want to come up with the optimal number for polynomial features. Other than that, there's not much to tune here. Okay, so what I wanted to talk about, this custom grid, right? So the custom grid thing is pretty much the same thing that we had in the scikit-learn package. It's a dictionary, right? So you have to pass the keys and items in a dictionary. So for example, if you're doing random forest, you can do max depth. That's your key, and the value is you can go provide a list of max depth of 2, 4, 10, 20, right? So we can literally give it a custom grid search, and so it comes with both pros and cons, right? So the advantage is that you can make sure you explore all the values for hyperparameters that you want to consider. So that's the advantage. The disadvantage is going to slow down the process for sure. For example, if I have, 4 hyperparameters and each has 3 values, so what do I get? 3 to the power of 4 different combinations, right? 3 by 3 by 3 by 3. So, and then it's going to slow down the process. By default, it's going to do a random grid search. PyCaret is going to do a random grid search, which is a lot faster. But the caveat is that it does not guarantee global, let's say, global optimal value for your hyperparameters. Okay. All right. I think again by default is connected to the scikit-learn and the optimization, tune scikit-learn, and etc. Okay. So let's see what else. Yeah, we can add some early stopping, max number of iterations, and all those good stuff that you could do with the scikit-learn package. So I'm not gonna go over the things that you already know from the scikit-learn package. All right, so that was the tuning part. Okay. So the next cool thing with PyCaret, so this is, if I use PyCaret for one reason, that's for the visualization part, because under the hood it's using a couple of very powerful visualization Python packages like Yellowbricks, which is for machine learning visualization. And I love the features of visualization when it comes to PyCaret. So it's literally save you 10 or 20 or 30 lines of code sometimes. For example, if you want to do the decision boundaries in classification, it is easily 20-30 lines of code. And then with PyCaret, it's just one. So I love this feature of PyCaret. Okay, so let's see what we want to do. We want to plot model. So let's go ahead and pull up the documentation, plot model. All right, so I'm curious if the installation is completed. Let's go back and see if the installation is done. Oh, so something is going on, right? So it shouldn't take that long. So if I were you and I got, 20, 30 minutes into it and it's still running, I'm gonna stop it and run it again, or connect to another session, or do something, or run it locally, right? But again, for this presentation, we're gonna skip. I will make sure that for the classification presentation, I will run it locally and try some of these things, coding it on the fly. Okay, so we talked about tuning model, plotting things. Okay, if you want to see what are the plotting options for regression, let me see if it is in the documentation. If not, it is already here. I also put it in the PDF that I put together. So if you go to my Where is it? Yep. So if you scroll down, the plotting features for, yeah, this is the plotting features for regression, for classification, and for clustering. So we are going to go over these ones now. Okay. Again, you can get access to those plot names here as well. Okay, so this is for regression, right? So yeah, we can look at, for example, residuals, right? So, well, if I do residuals, it's a residual plot. I can do residual interactive. It's an interactive residual plot. I think for Google Colab, you have to add you have to install another package. If you go to the installation part, they already tell you what was that thing. But for you, if you're doing it on a local computer, I don't think you need it. But again, I'm gonna try it next time in the classification, the notebook, and show you how to do that. So residual plot, error plot, Cook's distance, recursive feed selection, learning curve. This is important for machine learning, so we are going to talk about the validation curve, manifold learning, basically lower dimension of the data, feature importance. This is really important, and then we can look at the parameters, right? So this is another way that we could do. We could look at what are the hyperparameters of the model, right? For example, if you're and this is tree, if your model is a tree base, you can look at the decision tree. Okay, and that's I think everything we need from the plot thing. So let's go see the outputs. Okay, so I'm gonna start with remember, for example, I'm gonna plotting the XGBoost thing, right? This is the model that I created, and we want to plot things for the tuned version. I'm gonna compare tuned version and untuned version for some of the plots. So the first thing, if I don't put anything, by default it's gonna, for regression, it's gonna give me the residual plot. I could go ahead and do plot is equal to residual. Just make sure that the spelling is correct, right? So residuals, yeah, something like that. Again, by default, it's gonna plot the residual for you. There's no S. Interesting. Yeah, give it a try, because here there's an S, here there's no S. But I guess if you don't put anything, it's going to give you the residual plot. Okay. Okay. So this is our residual plot for the train set and test set. Remember, this train set has 70% of the 900 observation. This is 30% of 900 observation. Okay. We are not talking about that unseen data at all. During the entire process that we are doing, we don't touch the unseen data. We're going to save it for the very last part when we have finalized the model and we want to deploy it, or basically we want to make prediction. And we want to see how it performs in the truly unseen data. This is the distribution of the errors. And we can talk about the assumptions of classical linear model assumption, if it is linear regression, right? So this is the XGBoost, so we don't need to be worried about that one. But basically, we can see if the errors are normally distributed or not. Yeah. So that's the residual plot. Then we can look at the error plot. Again, so this is your y versus y hat. If everything is along this 45-degree line, it's a good prediction. Again, this is not necessarily good performance, because our observation is only 900, 70% of that 900, and in models like XGBoost, they usually require more observations. Okay. And we can look at our friend feature importance. So this is a feature importance. Again, guys, I'm not going over the theory of all these things. I assume that you already know it, and I'm going to show it quickly how you can do them, right? So this is a feature importance plot. For this example, it seemed that hours was the most important one, and then working days or not, and then year. Yeah, that's the feature importance. You can play around with how this feature importance is being done. For regression, by default in scikit-learn, it's looking at the total reductions from the mean squared error. And for classification, there are different ways that you can play around with. We can plot the parameters. So the parameters for my tuned XGBoost are these. So for example, let's look at the max depth. If you find, the max depth was 6. The max leaves, well, it was left to 0. Yeah. So these are, if you're curious what is happening behind the scene for your XGBoost tuned version. Okay. Then I can go ahead and plot the learning curve. So the theory, why you're interested in doing the learning curve, again, at a very high level, I explained it to you, but if you're curious, you can check out some online resources. What is a learning curve? So basically what learning curve shows you is it's plot the training performance, the model performance in the train set versus cross-validation, right? So imagine, I don't know, let me give you a very hypothetical, simple example. Imagine I'm using only 2 observations, right? If I only use 2 observations, and literally 1, 2, and if I use the train sets with 2 observations and I apply the linear model, so that linear model can go, so imagine this is observation number 1, observation number 2, that linear model can pass through that both lines, both dots. So what is the R square of that simple model? It's going to be 100%. So as I increase the so this is for tune XGBoost, it should go down, right? As I increase the number of observations in the train set, the performance of the model in the train set is going to deteriorate, right? So let me actually show you learning curve, machine learning. Okay. Well, we usually see something like this, right? So as you can see, the performance of the model in a train set is going to be good. As we increase the train set size, the performance is going to decrease. I want you to think about that extreme example that I gave you. If I only have 2 observations or 1 observation, I'm using linear regression. What is the R squared? It's going to be 100%. So if the sample size in the train set is a small, we're going to always start from 100% R squared, and then it's start decreasing. But for cross-validation, we know that we're using cross-validation, so the model has not been tuned to the cross-validation data, right? Because the model has not been overfit to the cross-validation data. So it's guaranteed that as we increase the number of observations, the performance in the cross-validation is going to increase. So this is very common, a pattern that we see in the learning curve. So we see something like this. Actually, this is interesting. We see something like this, that in the train set, the performance is going to get worse as the sample size increase. In the cross-validation set, the performance is going to get better. And as a rule of thumb, if we get something like this, it means that we have a high model variance. We need more observations. If I get more observations, then these two are going to converge to each other, and it's going to perform better. If I get something like this, it's very ideal, right? Because they converge to each other, and look at that. This is error. This is for classification. The error rate is relatively decently low. If I get something like this is concerning. It's telling me that the model has high bias, because even though they're converging, it means that in terms of sample size, it's okay. I have good enough number of sample size, but the error is very high, right? So for regression, if basically these two curves are so low, the R score is so low, it means that your model has high bias. Okay, so how can I read this one? So these two are converging. First of all, this is flat for whatever reason. I think that this tune XGBoost, I'm not passing a grid search, so it's not necessarily using the right hyperparameters. So maybe if I just use XGBoost instead of the tuned version of XGBoost, this starts to decrease. But the thing is that maybe we need to, this is a sign that these two are not converging yet, so maybe the sample size is small, and we already know that we only have 70% of 900 observations, right? 63%, 630%, 630 observations. Sorry. Okay, so again, this is what you can take away from the learning curve. This is a really important step in machine learning, and I encourage you to do it, because sometimes people are mistakenly collecting more information while they don't need it. So the model is suffering from a high bias, and they think that they can fix it by collecting more information, and the answer is no, you cannot. Okay, then we can look at the validation curve. So the validation curve, if I want to explain it at a very high level, basically tells you that those hyperparameter that you were tuning, is it overfitting or not, right? So so by default, it's going to look at score versus max depth here. And remember, in our tuned version, the max depth was 6. And it seems that it's not kind of overfitting. So remember, this is train set, this is cross-validation. I'm going to pay attention to the cross-validation score. And as soon as this cross-validation score, the performance is flattening, it says that maybe that's it. Maybe that was the optimal number for max depth. So here, it's not concerning to me, my max depth in the tuned XGBoost was 6, and this is from 6 onward is flattening, which is just fine, right? So I'm not concerned with that number. We're not overfitting. So that's basically how validation curve is used. But again, for models like XGBoost that you have too many moving parameters and hyperparameters, I usually don't do validation curve unless I specifically want to see what's going on with the max depth, right? Ignore this one because this is applied to the original data, the 17,000 observation, and in this visualization, in this notebook, I just wanted to show you work with a smaller data set. And this is manifold representation. Again, this video is becoming so longer than I expected, so I'm going to leave it up to you. Basically, this is a lower dimension representation of the data. And yeah, so the next step is evaluate the model. Okay, now let's talk about this evaluate model. When working with PyCaret, I usually don't do this evaluate model because it takes so long, especially if your data set is large. And you have already evaluated whatever you wanted to do, right? You did the plotting things, you did the compare models. The evaluate model function is gonna do it all at once, so it's gonna show you all those visualization at the same time, close to each other. But again, imagine you have all these visualizations, and just interactively you can click on them and see what's inside. But again, if your data set has 20,000, 30,000, 100,000 observation, this is gonna take so long, so I don't do it that way with PyCaret myself. Okay. So for example, here I'm creating a model, call it linear regression, and if I simply do linear regression evaluate that model, it's going to give me a nice, so here we cannot run it unfortunately. I make sure I do it for the classification example, but here our Google Colab has not installed the PyCaret yet. Okay, but that was the evaluate model thing. For interpreting, interpreting actually is interesting. Let's actually look at that. So we have evaluate model, interpret model. So interpret model again is taking a train model object and returns an interpretation plot based on what you want to interpret, right? So for example, what is it? Let me actually find the documentation. Yeah, under the hood, it's using SHAP package. SHAP package stands for Shapley Adaptive Explanations, which is unified approach to explain the output of any machine learning model. So I'm going to give you an example, but if you wanted to see the details, just go through this SHAP documentation. There are some cool things that you can interpret from the SHAP package. Okay, so one of the most common things that we report for interpretability is SHAP values, right? So I can interpret, for example, a couple of them here. So remember, I'm going to apply this interpret model to my tuned XGBoost, and imagine this is the SHAP values that are generated, right? So we have feature values, the colors of feature values, low level, this is low feature values, high feature values, and SHAP values can be negative or positive. Negative, it has a negative impact on your target target variable. Positive has a positive impact on target variable. So let's interpret it. It's going to make a lot more sense. Let's look at temperature. Okay. So temperature, I know that blue temperature are what? Low temperatures. Red temperatures are high temperatures. And the blue ones are to the left of zero value of SHAP. So it seems that the blue temperature, the cold temperature, is going to negatively impact the number of rental bikes, which makes perfect sense. The red temperature, basically the high temperature, is going to positively impact your rental, your target variable, the number of rentals, right? And you can look at the distribution as well. So this is along with what you can do with simple linear regression, but it is more informative, right? Maybe quantitatively it's not what you want. So for example, I cannot say what is the effect of temperature on the counts using simple linear regression, because remember, linear regression is the most explainable and simplest model out there. But this doesn't mean that my XGBoost should be complete black box. So I can still do some level of interpretability here. All right. Now, the rest of this notebook is actually for those of you who want to have fun and win some competitions, right? Because usually, look at that. Our tuned XGBoost got us to, what was 85-ish? 85 R-square, 85% R-square, right? And imagine for a Kaggle competition or just for fun, you want to increase that prediction by a percent or a couple of percent. And this is usually what you get by ensembling, blending, or stacking models. And you usually, again, 1 to 2%, depending on what level you're starting from, right? Here we are starting from 85%. By blending, we can improve it a couple of percentages, I guess. But that 2% is gonna cut it, right? It's gonna make you the winner of Kaggle competition. So the rest of this notebook is optional, but I highly encourage you to stay with me if you're interested in this kind of approaches, right? So what do? There are three terms that we use: ensembling, blending, blending and stacking. So what are they? So ensembling, if you know what is random forest, you already know what is ensembling, right? So ensembling is a common machine learning technique used to improve the performance of models. Basically, wisdom of the crowd. Why not taking advantage of wisdom of the crowd? So I have one weak learner, let's say a decision tree, and I want to make a forest of these decision trees. I call it random forest, and make it a strong learner, okay? So that strong learner is an ensembled version of a bunch of weak learners out there. So let's take advantage of the wisdom of the crowd. And we can do bagging and boosting for that, but again, I'm not gonna go over the details of these two. If you're curious, just check out the conceptual videos. So that's the ensembling things, right? So I can ensemble, I can imagine my weak learner's decision tree, and I can create a model ensemble. This is my model DT decision tree. And I'm gonna ensemble that DT, right? So I say ensemble model DT. Of course, you can say how many estimators you want, how many weak learners you want to use, and etc. I'm gonna show you the documentation in a second. And I can do the bagged version. By default, it's gonna do bagged version, but if you change the method to boosting, it can do the boosting version as well. And so that's the ensembling. Let's look at the documentation for ensemble. It should be here. Okay, so again, by default the method is bagging, but if you can change it to boosting as well. So let's see. The number of estimators by default is 10. So it's gonna, for example, if you want to think of it as a random forest type of things, I have a weak learner called decision tree, and by default it's gonna put 10 of them together and then make it an ensemble method, right? The performance of this model is usually better. The variance is going to be smaller because the trees are decorrelated, and etc. etc. Again, the theory is a little more involved. I encourage you to watch the lecture videos for random forest if you want to get a good sense of what is ensembling, what is bagging and boosting. Okay, so that was the ensembling thing. Now let's talk about blending and stacking, the very last two powerful, basically putting models together for better performance type of agenda, right? I can go ahead and start with blend, and then we will do the stacking models to just wrap it up. So, all right, so what is blending? Imagine I have three models, model number 1, number 2, number 3. Let's say XGBoost, Light GBM, CatBoost. All right, let's keep it simple. Let's say I have random forest, linear regression, and XGBoost, right? Each of these models, and I want to blend them together. Each of these models are going to make predictions. So let's call it Y hat. This is a prediction for random forest. Y hat for XGBoost. Y hat for linear regression. If it is regression, I can take the average of all these y hats, right? So I have a y hat 1, y hat 2, y hat 3. Again, y hat of XGBoost, random forest, linear regression. I take the average and I call that the prediction of the blended model. So that's what we mean by blending. I hope that's clear. Stacking is also some sort of blending, but it's gonna do one more step. So in stacking, let's say we have the same three models: XGBoost, random forest, linear regression. Y hat XGBoost, predictions for XGBoost. Y hat random forest, Y hat linear regression, right? And then I'm gonna use those three columns of regressions, and then I use those as new features and I use it in the meta model, right? So this meta model is basically using the predictions from the previous models, from the three models that I just named, as new features. So this is the difference between blending and stacking, and the whole idea is that somehow mix these models, right? Ensembling, blending, stacking basically is different ways of mixing different models to improve the performance of the model. And at the core of it is they're going to reduce the variance of the model, and that's how we hope that we can get better predictions. But remember, in all these models, if the models are suffering from high bias, there's not much you can do with it. If you blend a bunch of bias models, if you stack a bunch of bias models, it's gonna still be biased, right? So here I just want to remind you what was the top three. So the top three was, I'm going to show you some visualizations. Hopefully it helps you better understand what is blending versus stacking if the explanation was not clear enough. So remember, my top three performers were XGBoost, LightGBM, and X33 regressors, right? I'm going to say blend these models, okay? Blend these models, and what is the list of my estimators? These three. No, I can say top three. I can pick whatever model I want. I can say just blend random forest, XGBoost, and linear regression. But here it makes sense to blend the top three performers because the top three performers probably are going to blend better with each other. But again, nothing should stop you from mixing these models differently, right? If I use this blender, the performance of the blender, and again by default it's going to use tenfold cross validation, is 84.44. It's not that bad, right? So, and as you can see, so this is the visualization of the blender. I have XGBoost, LightGBM, and X33 regressor. It's going to take the average of all these predictions and call it your prediction. Okay, so that's for the blender. Now, let me see if there's anything extra in the blender that I missed talking about. Yeah, you passed the number, the list of estimators. Optimizer, yeah, again by default you can, for example, say, okay, blend these models and optimizing R-square, optimizing RMSE, right, and things like that. And for classification it makes more sense to change these optimize, but for regressions usually get consistent numbers along RMSE if the data set is well behaved, right? And yeah, I think that's pretty much it about the blender and stacking thing. We're gonna stack models like this. Let me show you an example here, and then we're gonna check the documentation if you wanna to check if I missed something or not, right? So for stacking thing, how do we do that? I'm gonna, for the sake of argument, I'm gonna stack the same models, the top three performance: XGBoost, LightGBM, and linear regression. Oh, not linear regression. What was the third one? Yeah, the X33 regressor. And the performance of the stack here is 84.45. I think it's pretty much the same. Well, maybe slightly better for the stacker. Again, remember guys, the number of observation is ridiculously small here. It's only 630 in the train set, but we know that if we increase that observation, it's going to help us getting a better R-square, and probably stacker is going to outperform blender. But I think the structure of this stacker is going to help you understand stacking better. So remember, we are stacking XGBoost, LightGBM, and X33. So this has a Y hat, this has a Y hat, this has a Y hat. Let's call them Y hat 1, Y hat 2, and Y hat 3, right? So the way that we're going to stack them together, I'm going to use these three columns as three new features, and I'm going to apply a final estimator to these three features, right? So now my regression is going to be regressing, let's say, count number or Y on Y hat 1, y hat 2, y hat 3. What is the model? What is the meta model here? The estimator for the meta model is linear regression. So you can change this estimator for meta model as well. So this is one of the features. Okay, so that's basically how stacking thing is doing the job, right? So for example, I can say I have XGBoost and I'm gonna stack top 3 with my XGBoost. And remember, XGBoost was already there, but my meta model now is XGBoost. So at the very last layer, it's not linear regression, I'm using XGBoost. So if I show you the pipeline, something like this, I have XGBoost, LightGBM, XR3, and then the meta model is using XGBoost as an estimator. And look at the performance. The performance is a lot worse compared to when I use the linear regression as a final estimator for the meta model, right? For linear regression, it was 84. For this one, it is 73. Okay, so yeah, that's pretty much it. I think it's everything we needed to know for creating models, comparing models, tuning models, plotting things, and yeah, ensembling, blending, and stacking. So maybe few touch-ups here and there to just make sure that we talk about the predictions and etc. Right? So the AutoML, there's this function called AutoML. Again, this is one of those things I don't recommend using it because it's going to take so long. And by now you know what model is performing best, so you can keep track. But what AutoML is going to do is that, let's say in this notebook you created, I don't know, 20, 30 different models, and at some point you lost track of what was the best performer. So you're going to say, you know what, do AutoML to the entire, so if I don't pass anything, it's going to look at the entire estimators that has been trained previously in this notebook. So, and then give you the winner, what was the winning model, right? But again, we usually don't need to do it this way. And yeah, that's pretty much it, what the AutoML is going to do. So and again, you can say, I can say, save my best R-square model and look at the AutoML and tell me what was the best model, save it as best R-square model, and plot it. It turns out, not surprisingly, because we knew already, that this stacker with using linear regression as a final estimator in the meta model was the best performer, right? Again, no surprise here. We already knew that. Okay. So the last part is a prediction. Let's go ahead and make some predictions. I can say, I know that my stacker is the best model, so let's predict that. So let's predict model using a stacker, right? So I'm gonna say, and I'm gonna make, by the way, actually, let me go ahead and pull up the predict model thing. Predict model, let me search it. Predict model. Okay, yeah, this is a predict model thing. Okay, so for the predict model, you have to pass the estimator. Okay, so you want to make predictions, what model do you want to use? That's it. You have to pass the data, right? And yeah, if I don't pass anything, by default it's going to use the holdout set. Okay, so what do I mean by that? So as you can see, if I just say from this experiment number 1, just make some predictions, use the stacker model because I already knew that it's the best performer, and if I don't pass anything here, it's going to use this for the holdout predictions, right? And remember, the holdout predictions are the 30% of that 900 observation, right? 30% of the data that you created, right? This has nothing to do with the unseen data, right? So it seems that for the holdout predictions, the model is doing 83%. This is a decent job, right? And then let's say you're happy with this model, you're happy with your stacker, which was the basically mix of 3 top performers, right? Now you want to finalize things, right? And I think I talked about the finalizing things in the introduction video, but again, it doesn't hurt if I talk about it again. So what's the difference between finalizing and then predict model? So the finalized model, let's say you're happy with the performance of the model in the holdout set, in the test set, and you want to call it the winner model, right? So I'm going to give it a name. I call it final stacker, and you can call it anything. You can call it, imagine this is casual competition, you call it the winning model, my winning model, right? And again, from experiments number 1, I use the finalize model function, and I pass the stacker. So what this step does is use the entire data set, the entire 900 observation, and rerun the model and make some predictions and call it final stacker, call it your final model, right? So, and you can visualize this final stacker. Again, no surprise here. This is the entire pipeline, and we are using XGBoost, LightGBM, and extra 3 regressors, and at the meta model estimator, we're using linear regression. Okay, now we're done. We're literally done. If you're doing a carrier competition, you pass the train set, and you just do the cross validation. You can make some predictions for the holdout set. But what you need to do is you also make predictions for the unseen data as well, right? So do you remember we kept 10% of the entire data as unseen and we never used it? So that's why basically we did that, because now that we finalize the model, we want to see the performance of this final version of the model on something that the model has absolutely not seen at any step, at tuning, at cross-validation, never, okay? So this is how we do that. We're going to use the same function predict model. Now I have to say, okay, data is not the test set, is not the holdout set, it's my data unseen. So we can look at the predictions, and we can basically look at the tail of these predictions. And this if I use the data unseen, it's going to give me a table like this. And remember, guys, this is the unseen data set. This is what the model predicted. It's going to call it predictions label, but again, you can rename it and call it anything. So when the count was 445, the model is doing this. When the count was 4, the model is doing minus. And again, so this is one of those things that we could play around with. We could just say the predictions should be positive, right? And right now we know that these negative predictions don't make any sense. Doesn't make any sense. Well, there are a couple of things going on here. First of all, the sample number of observations was small, so probably with the higher number of observations, we get less of these negative numbers. And secondly, we could truncate the predictions outcome as well, right? And then, yeah, for example, in deep learning, we could use some ReLU activation function to make sure that the negative numbers are truncated and things like that, right? Yeah, that's it. We finalize the model, we make some predictions in the data unseen data set, and now we're gonna go ahead and save it. So how do I save it? So I just use from experiment number 1, save my model. This is the model, final stacker, give it a name. This is gonna save it in your local drive or whatever it was. So if you're doing it in Google Colab, so it's gonna save it here. Right now, again, if I run this one, I wish the installation was done. We could showcase this, but if I press this one, it's gonna make by default it's gonna make a PKIL file. PKIL is a Python file, and then you can load it later on, right? So it's gonna be saved. You can download it and put it wherever you want. Then you can load the model, right? For loading the model, look, pay attention, guys. For saving the model, you have to save from this experiment number 1. But when you want to load the model, you don't need to say, okay, load this from experiment number 1, because it really doesn't matter, right? You already know that it's a PKIL file coming from experiment number 1. And you can load it, and you can quickly look at the pipeline of the loaded model, and etc., etc. You can deploy it on cloud, on AWS, Google Cloud, and Microsoft Azure as well. So there are some details about the deployment of the on the cloud, and maybe running different experimental logs and things like that. But I think this explains at the very high level what is PyCaret and how we can do machine learning regression using PyCaret. I know it was a relatively long video, plus 1 hour, but I think we covered A to Z, whatever you needed to maybe get to top 5 or top 10% of the Kaggle competition. So just give it a try, play around with it, and let me know what you think. But keep in mind, you should use PyCaret as a benchmark, okay? Do not use it blindly. Again, for fun you can, but for real world projects, you should exactly know what's happening. And I encourage you to use it as a benchmark. See what is the best performing models like this by looking at this, and then try to dig deeper in the winning models. Okay? Until the next one, take care and see you soon.